The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hi everyone, we're going to get started. So today it's another lab day, so we're going to split up, and half is going to be outside again, so hopefully brought your coats. If you haven't, you should start learning, that's a good thing to do. And then the other half in the shop, finishing up the woodwork you did, and then we're also just going to do some metal work and PVC work, just so you get familiar with all the tools in the shop. For the pumps, I think Amit's going to talk a little bit. I just wanted to mention, someone asked, is a foot pump always better than a hand pump? And the answer is no. There's a variety of reasons why you might want a hand pump over a foot pump. One of them that's a little subtle is that in some cultures, it's not acceptable for women to stand over water sources. And so you can't use a foot pump as a woman, and so if the woman needs to be able to do the work, she has to use a hand pump. So there's many places where foot pumps have not worked because of that reason, and hand pumps have worked out great. So and Amit, I think we'll talk about some other reasons, but there's a lot of variety in what's going to work better, where, and why. So yeah, it's not, while you guys were calculating power, and that's what we're a little obsessed about in this class, that's not the only thing you have to worry about is maximum power.
Okay, so addressing the rest of the pump questions. When you're actually trying to decide what kind of pump to implement in a specific site, there are a few things you need to take into consideration. First, you need to figure out how much water is going to be used. If you're going to pump a bucket of water a day, building an expensive rocker pump doesn't really make sense, and a hand pump will do the trick. Whereas if you're trying to irrigate your entire field, then maybe a cement pump is a better alternative to the hand pump because you don't want to sit there pumping with your hand for hours and hours and hours. That being said, the other thing is that different pumps can pump different amounts of water and can pump over different pressure heads. So the cement pump is a diaphragm pump, and I think it can pump about 5 to 7 meters deep only. So it's not really used to pump water from a low water source like a borehole or something like that, because it just won't be able to do that. A little bit about how it works is you have 2 valves, and then you have this sort of, it's called a diaphragm, and then you have another valve here. And so what happens is this thing can change anywhere between this height and this height when you step on it. And so when you step down, you're constricting the volume here, and water is going to get pushed out of here into this from your outlet. And then when you release it and you push up, this valve closes, and then there's a pressure difference in here, or negative pressure in here, which will open this valve and pull water in. So it works pretty much the same way with 2 one-way valves, but the thing is that you can't generate that big a pressure difference, and that's why you can't pump over that, or you can't pump that deep. And so that's another one of the considerations you have to take into account. I think when you want to pump from boreholes or something, you want to get somewhere around 50-ish meters deep. I know the hand pump that we went over the other day pumps somewhere between 20 and 40 meters deep. And the treadle pump, which you may have seen in other places, it's similar, but instead of rocking back and forth, you lift up your legs up and down kind of like this. And it's the one that IDE uses, and it's mostly used for irrigation of fields. And that one I know pumps only 7 meters deep. And I lost my, cool. Yes?
Have any of these pumps been used for filtrations and sanitation kind of purposes? Or just carrying and moving water? Like, can you put a filter, seems really rudimentary, but can you put a filter at the end of one of them, kind of like a valve, and then just collect its dirt?
I've seen people use pumps with filters on them, generally larger pore filters. But the problem with that is you normally have to replace the filter every so often, and you don't want it in an internal part of the pump because it gets tedious to replace it all the time. But I've seen people put like just cloth filters over the end to get rid of turbidity.
Great. So it's because a pump is pushing out a relatively high pressure and filters tend to work slowly, it's rare that you can just put a filter at the end. So typically, while it would be great to just have point of use water purification and cleaning, apart from like turbidity factors, it's hard to do that effectively.
All right. So yeah, so those are I think the two biggest questions from last week's lab. Do you know if you have more questions about last week's lab? Cool. So a little bit about what we're going to do today. The objectives are we're going to try to learn about how to get energy from solar panels, PV panels. So you're going to be working with them. We have one that's this size and one that's maybe 3 times the size of this. So we're going to take these outside and hook them up. And then we're going to learn about a little bit about the theory behind not actually how the PV panel works. We'll go into that later, but this is more about how to use the PV panel and some applications that come from that. We're going to learn how to hook it up to a battery because that's one of the most common uses, I think. And we're going to look at some of the design considerations you're going to have to take into account when you look at designing a solar system. And so that's sort of one half of the lab, and the other half is going to be working in the shop again, and you're going to learn more about fabrication techniques, but this time instead of working with wood, we're going to look at other materials like metal and PVC and sheet metal. Cool. So, where's my sheet? Okay, so when you're trying to get energy, when you're trying to get power from the sun, you basically have your sun, and then you have the surface of your Earth, and rays coming in. Do any of you know how much, best case, when the sun is shining, there's no clouds blocking the way, what the best case power you can get from the sun is in watts per meter squared? Yeah, it's about 1,000. Now at the beginning, at the first class we sat in, we tried calculating the average daily electrical consumption, or average electrical consumption per year for people living in the developing world. And based off of those numbers, we have, you can approximate that people in Nicaragua use about 1 kilowatt hours a day. And then people living in Haiti use about 0.1 kilowatt hours of electricity a day. So if we're looking at solar, we're looking to power all of these, the 1 kilowatt hour or 0.01 kilowatt hours that people are using in the developing world using this energy. How much surface area would we need to harness the power? So we can walk through it, right? And we get and then you know that a day has 24 hours. So you can multiply that out.
The sun doesn't shine for 24 hours though.
Yeah. It's true. I'll get to that in a second. So you get about that much surface area where you need. So if you could ideally harness the power of the sun at this efficiency, or at this much power for 24 hours a day, for one day you would only need you would only need a collector that's 0.04 meters squared, which is pretty tiny, which seems like a really good idea. But there are a lot of there are a lot of reasons why this is not the right way of figuring out how much power you need. So like you said, for example, the sun does. How far down can you guys read it again? Is it about here?
The lower. There.
There. Okay. So yeah. So let's brainstorm some of these ideas or some of these reasons.
The maximum isn't always 1,000 watts. Due to the angle of the sun or time of season.
Some people are gonna want more than 1 kilowatt hour.
Yeah.
So supply and demand is not always exactly matched. So there's no storage. In our equation right now there's no storage yet. So there might be fluctuations from 0 to 1 kilowatt hour
Okay.
during the day.
You get like max about 30% from photovoltaics.
That efficiency goes down even more as the panels age, and also if it gets any scratches or anything on them.
Okay, so let's start looking at some of these and quantifying some of these constraints we have now. So we can't do this anymore. Let's still work with these numbers as ballparks because, I mean, we're only really concerned with order of magnitude estimations really for this. So efficiency of PV, at max you get about 30%, but I think that's sort of the laboratory, like cutting grade technology that is really expensive. With commercially available PV, it's somewhere between 8 and 18% is what you're gonna get right now. Yeah, we're not gonna look at that one yet. So this one, about how many hours do you think should we approximate the sun to be up a day?
Well,
I guess that goes with the whole model, is it being maximum
10 hours, maybe.
Okay, so let's go 10 hours. I think that's still a bit high. I think somewhere around 8 is better.
Yeah, and this is assuming equatorial.
Let's go 8 hours. And then storage is also a big factor that, I mean, that you have a huge amount of energy loss in storage as well. There's like, this is one of the reasons why just energy is a problem, because we have no really good way of storing it yet. So generally, when you are trying to get power from your solar panel, you're going to try to charge something with it, like a battery. And when you charge a battery with it, you have built-in losses. And the efficiency of transferring power from a solar panel to a battery without using any sort of voltage regulation or anything, because that has energy loss too, is about 75%. And so now that you've stored your energy, what sort of applications are you going to try to power off of this battery? Generally.
Like small appliances.
Yeah, and what kind of power do small appliances take? Are you going to AC? So you're going to have to convert this, because when you have power stored in a battery, it's stored as DC. So you have to convert it to AC again. So you have this DC to AC conversion, which also has a loss in efficiency. And then we can say that's about 75% too. It varies a lot depending on how expensive your inverter is and like how you're matching your loads with that inverter. So it goes anywhere between like 50 and 90%, I'd say, but sticking to 75% is reasonable. So now that we have all of these numbers, we can reevaluate our calculations. So we have 1 kilowatt hour still for Nicaragua, and now we're dividing it by times 0.75. I think we want them in the denominator. Yeah, let's do this because I'm running out of space. And let's just say that that's 10%.
One over the lifetime of the active should you take the efficiency?
Sure. Okay. And does someone have a calculator and want to do this? I can do it on my computer too. Let's race.
Go, Jack, go. 0.002777778. Probably 0.7 actually.
I think that's in the, well, it's kilowatts divided by that, so it's actually going to be 2.7, or whatever. It's going to be about 3 meters squared.
Yeah, 2.7.
Yeah. Which is suddenly a lot larger than what we had before. And this is still assuming that this is going to be best case scenario. And so if we assume that the sun is going to be shining bright every day, we're going to have a solar panel at least 3 meters square, or 3 square meters. And then we have to think about other things too when we're dealing with PV usage, like what is the power being used for, and how reliable does it need to be? So, what are some places where we could think about installing solar panels where it wouldn't need to be reliable and it would need to be very reliable? Okay. I guess in the non-reliable, maybe a home where you don't, if you have a house that's not using refrigeration and they're using lighting, if they don't have electricity for one day or something like that, it's not the end of the world. But when you're looking at designing a solar photovoltaic system for a community partner, you need to be asking these sorts of questions, like how long can you go without power? For a hospital, if you can't go a day without power, what do you do if there's no sun for a week? If it's cloudy, you can't have people who are on technology, or you just can't have that for the hospital. So you need to build a more robust system that can draw more power and store it better. Whereas for housing, maybe a couple days, if not, or maybe you can afford to go without electricity for a couple of days. So yeah, and then does anyone know what the cost of photovoltaics is as well? Yeah, when we were looking this up, we found a pretty big range for how expensive they were. I think most of the sources were saying it was around $3 to $5 for the cheapest PV we could find, but it's still on that order for watt. And so I guess the thing you should take away from this is a lot of times people look at lighting and just say, or electricity, and just assume that solar is like a miraculous solution that's going to solve everything, and you really don't want to think about it as that. You want to actually think about all of the considerations that go into creating a system. So now I'll show you. This is a solar panel that we got for D-Lab. We have 2 of these. Basically, you have a positive and ground coming out of it, so you can hook it up to a load. But if you want to hook it up to a battery, you have to somehow regulate the voltage before you're doing that. Because if you plug this in directly to, well, what'll happen if you're trying to charge a 12-volt battery, and the solar panel's outputting about 20 volts, and it's a lead acid battery, like a car battery that you're trying to charge. It'll probably explode. I think if you drive too much voltage or through a car battery, you're going to end up producing hydrogen and oxygen as byproducts, and it's very flammable, and if there's a spark, then it explodes. What about the opposite case, where your solar panel is outputting 8 volts or something like that, or 6 volts, and your battery is trying to take 12 volts?
It'll never charge more than that.
Yeah, more so than that though, not that it's not only going to charge, but your solar panel is going to discharge your battery. So you're going to do the opposite. So you need to build in some sort of regulation for it. You're going to have a voltage regulator that makes sure that you're outputting the right amount of voltage, and then you also need to make sure that you have a diode in there somewhere so that electricity doesn't backflow and drain the battery. Luckily for us, instead of having to design and build all of these things, there are companies that do it for us. So we have a couple of these solar controllers. And so they have this stuff built in, so you can hook a solar panel up to 2 ends of this and your battery up to the other 2, and then you can charge a battery from that. And this is just, there are 2 different ones. This one takes, this one you can put a load directly onto as well. And the last thing I was going to talk about are resistors and potentiometers. Do you guys know have you guys seen potentiometers before? Okay, yeah. So what a potentiometer is it's a variable resistor. And so this thing is a resistance, this thing has uniform resistance that changes linearly with how you turn this. So if you're over here, you effectively have a resistor that's this long, and then when you open it to this far, you get a resistor that's twice as long. And so you can change the resistance anywhere from 0 to, this one's rated at 500 ohms. And it's kind of like what we did the other day with the resistance. The resistance is equal to rho L over A. So you're just changing L and getting more resistance. So the way you use these, you're going to use them later on in the lab, so I just thought I'd explain it right now, is you hook up to these 2 terminals. If you hook up across here, you're just going to get the full 500 ohms. And if you hook up to here, as you sweep this across, your resistance will go up. And when you guys are doing the lab, remember, I wrote it as a note and I'll explain it again there, but remember that when you're measuring the resistance of this, you want to disconnect it from the solar panel, because if you don't, you're going to fry the voltmeter. And it's not, we don't want you to fry voltmeters because they're expensive. And we only have 2 right now. So do you have any questions about what we talked about right now? Okay, so we could split into 2 groups.
Yeah. Okay. So everyone can sit down.